So that is Safir. How are you? Third time finally. Yeah, all of them are there. Yeah, you should. They should know how it's like to meet a legend. Yeah, cool. Oh, okay. Mic check, am I audible? To at least the folks on stream? Mic check. Check 1, 2, 3. Is that fine?
इधर खड़े
Okay. Good. All right, yeah. Good afternoon, folks. Thank you for coming all the way here to spend your Saturday with us. I don't know how it's the third edition of the Platform Engineering Meetup. When we first started off, the whole story began when, before COVID, we used to attend a lot of these meetups. And post that, we really saw sort of a lack. Usually there'd be these big conferences that you just see in a year, be it like RootConf, KubeCon, all of that. But we felt, Zainab, Talina, I, as well as Safir, who's been the torchbearer at least, we thought it would be a good thing to start a community where we find sort of like-minded folks who'd probably take their Saturday to spend time with us and come to know more, as well as, have others who would like to present their work. And this work is not always something that is orthodox. It can be very unconventional. So with that, I'd like to thank our sponsors, for all the folks on the stream. Yeah, we'd like to thank Cloudflare. And for the venue, we'd like to thank Quintype, as well as, our reviewers like Sudhir and others in the panel. Apart from that, we'd like to thank every one of you. And I'm sure that, you will love to see what these speakers have to say. So yeah, who's hungry? To start off, we will have this talk by Eternal or Zomato, where they talk about how they probably scaled from their backend event-driven system to accommodate all of the orders that are flowing in. So without further ado, I'd like to introduce Dev and Sakib. Please take it away. A round of applause.
Right. So hi everyone. Good afternoon. My name is Dev. I'm an SDE at Eternal, part of the Zomato SRE team. Sakib and I are going to present this talk today. So in this talk, we'll first understand asynchronous consumer architecture and why it matters. We'll look at some of the issues we faced with our legacy consumer setup and how we solved them by creating our own consumer proxy platform known as Worker Controller. Then we'll go through some of the architectural choices and features of Worker Controller, and we'll close this talk with its current status and future plans. So first, let's quickly understand synchronous versus asynchronous processing with a simple restaurant analogy. Imagine a restaurant that does synchronous processing. That is, it processes orders strictly one at a time. It only takes the next order once the previous one is fully completed. So in this case, even if some counters are free, they can only accept new work once the current order finishes. This leads to idle resources and a lot of unnecessary waiting time. Now imagine a different setup, a restaurant which does asynchronous processing. Here, orders are placed into a queue, and each counter independently picks up work from this queue. So here, no order blocks another, and counters always stay fully utilized. This improves the overall throughput and reduces waiting time. So when we place an order on Zomato, we get the order place screen within a couple of seconds. But behind the scenes, we have to do a lot of other stuff as well, like notifying the restaurant about the new order, assigning a delivery partner for the order, sending SMS notifications, etc. Many such flows are executed asynchronously. there are multiple async consumers which are responsible for handling these flows. So for us, async consumers are as important as sync microservices to complete an order lifecycle. Now let's look at some of the issues we faced with our legacy consumer setup. So to deploy with confidence, each service has a funnel. First, we do local testing, unit tests, testing on dev and pre-prod environments, and as a last final line of defense against bad deployment, we have canary. So canary helps us minimize risk of bad deployment by sending a small percentage of the actual live production traffic to the new version of code. As you can see in the image, the 1% of traffic is going to a container with the new code. So how does this work? This works because our service-to-service traffic architecture is push-based. This is powered by our internal Kuma service mesh. So using our service mesh or a load balancer in some cases, we can control exactly how much traffic is being routed to which version of code. But consumers are fundamentally different. They don't receive traffic via a mesh or a load balancer. The legacy consumer setup that we see here is pull-based. So each container is independently pulling messages directly from the queue at an arbitrary rate. So in this case, when we deploy a new consumer version, it immediately starts consuming 100% of the production traffic. So there's no gradual rollout. And there's no deterministic way to control or split throughput across different versions of code. As a result, implementing canary is extremely difficult. Apart from this, there are also other issues such as there's no standardization across teams and across consumers, making operational control tough. And teams would often tend to club multiple consumers in a single container, which would lead to high operational complexity and noisy neighbor issues where some issue in one consumer can impact another consumer in the same container. These are some of the snapshots of the production incidents we faced. There were recurring issues with common factors which our legacy setup simply could not handle. So this motivated us to make our own solution. So what problems are we solving? We want to solve canary for consumers. Apart from this, we are also solving for multiple other fundamental limitations in the existing consumer systems. For instance, scalability of Kafka consumers. As we know, throughput of Kafka-based consumers is limited by the number of partitions and their latency. Also, we want to ensure standardization across teams. We want to do poison payload handling by providing retry budget and DLQ by default, do graceful panic recovery, and provide gradual throughput control with adaptive circuit breaking. Now let's look at some of the possible approaches with which we can do this. So one option is to introduce a standard sidecar or a shared consumer library. Standard sidecar here would be responsible for consumption alone. And here, in a single container, we have separated the processing code and the consumption code. So we can easily achieve standardization using this approach. But there would be an added maintenance overhead of car in each of the containers. So scalability would be an issue. It's not the most optimal. Also, more importantly, this architecture is still pull-based. So implementing canary still remains difficult for the reasons we saw earlier. So it is clear that to enable canary, we need a push-based architecture. One way to achieve this is by separating consumption from processing. So imagine in this approach, we have introduced some consumer proxy nodes whose responsibility is to pull from the queue and push it to the upstream services for their processing. So this gives us two major benefits. First of all, processing nodes can now scale independently of the consumer nodes, and the architecture becomes push-based. So implementing canary is feasible now for these workers. So we have now solved the scalability and canary, both of these issues that we saw in the last approach. However, in this approach, we would need a separate consumer proxy to consume from each queue. So this would lead to high maintenance cost and additional operational overhead, and also a lot of resource wastage. As for us, only a small number of queues typically contribute to the majority of the throughput. As we can see, this is in our Kafka cluster, we can see that only a few queues are contributing to the majority of the throughput. So provisioning resources separately for all the bottom queues here would lead to a lot of resource wastage. So we don't need a separate consumer proxy for each queue, but we need a single consumer proxy which can handle multiple queues. So introducing worker controller. Worker controller is a multi-tenant consumer proxy which decouples queue consumption from payload processing. It can handle consumption from multiple queues, and it pushes the payloads to upstream workers via HTTP or gRPC calls. It can handle consumption from both SQS and Kafka queues. It also uses push-based architecture as opposed to the pull-based architecture of legacy consumers, making canary feasible for these workers. It also supports parallel processing for unordered Kafka workloads, which allows increased effective throughput per partition. So this helps us tackle the traditional bottleneck where Kafka consumer throughput is constrained by the partition count and sequential processing. So now we have solved the issue that we saw in the last approach. However, since one consumer proxy is now handling consumption from multiple queues, we have introduced multi-tenancy here. So this creates new challenges, such as how do we ensure fairness? Or how do we make sure that heavy traffic on one queue does not increase lag on another queue? So Sakib will now walk us through how we handle consumption from multiple queues and ensure fairness.
So hello everyone.
You can do it in the end.
Am I audible? Sure. So hi everyone, I am Sakib Malik. I am also an SRE at Zomato, and I've been working here for past 3.5 years. So before seeing how worker controller handles multi-tenancy, let's quickly see how a sample consumer config looks like in worker controller. So as you can see here at the top, process name is basically a unique identifier for a consumer job. And you can also define type of queue you want to consume from. It can be Kafka or SQS here. And you also have to provide client. Client is basically the RPC or HTTP method that is called via with the queue payload that is being given here. And you can also define rate limits such as maximum RPM. So multi-tenancy. So as we define, multi-tenancy is basically an architecture where a single application instance serves multiple tenants or processes while ensuring fairness for each of them. So in worker controller, we use Go routines. So for those who don't know, Go routines in Golang is basically like a lightweight threads. And in worker controller, we use Go routines as processors. So these Go routines are used to schedule processes, where a process is basically a combination of fetching from a queue and making an RPC call. Let's first take a simple scenario. We have a single Go routine, and we have a single process. We can just schedule this process on this Go routine, and 100% of the Go routine's time will be utilized. But in worker controller, as we are combining multiple such processes or queues in a single consumer proxy, let's take another example where we have two processes, process A and process B. We can assume both of the processes have same ingestion rate and same latency. Well, in that case, it's pretty straightforward. We can just do round robin over these two processes. Let's say now latency of process A increases suddenly. What will happen now? So basically, in that case, in last 1 minute, process A will take more time on the Go routine, and B will get less time. Automatically, consumption rate of B will go down, as well as for A. So specifically, lag on B increased because of latency increase in A. So we can say that fairness is not maintained among these processes. To solve the multi-tenancy problem, we somehow need to give both the processes equal time on the resource, which is Go routine. We can say that we have to give 50-50% of the time in the given time window. So even if latency increases, fairness is maintained. To solve this, we use completely fair scheduler, which is CFS. CFS is used by Linux for scheduling its processes, so we have used the same algorithm here. What CFS does is, it basically tries to give equal time on the resource, which is Go routine, and so that fairness is maintained. Let's see an example to understand this better. So here you can see virtual runtime is basically the time the process has taken on the Go routine. So up until now, both the processes have taken 2 seconds of time, and Go routine has been utilized for a 4-second total. Now let's say latency of process A increases to 2 seconds. Now process B will be scheduled more, and A will be scheduled less, so as to give them equal amount of time proportionally. This way of scheduling, or CFS, makes sure that each queue gets 50% of coroutine's time. As you can see, due to CFS, lag on queue B didn't increase, only queue A was affected. Now let's see how worker controller scales and some of the other features. Now previously, when we saw both processes had same latency, and both the queue had zero lag, so coroutines was busy all the time. So we can say that coroutine was utilized for 100% of the time. But as latency of process A increases, we only have one option. We have to increase coroutines, as we need more processing capacity. In worker controller, we track how much coroutines are working. That is called utilization. Based on this metric, we increase or decrease coroutines. So as we saw, scaling of coroutines in a single worker controller node, we'll now see how worker controller nodes itself scale. So worker controller has CPU-based horizontal autoscaling. And as we saw, when RPM increases, we need more coroutines to schedule them. So coroutines also increase. And in Golang, Go scheduler manages these coroutines over OS threads. So it needs resources to schedule them. So as coroutines increase, it takes more CPU to schedule them. And as CPU increases, worker controller nodes also scale. Now let's see how worker controller does rate limiting. So first, let's take an example where there is no rate limiting. Let's suppose we have a queue with an ingestion rate of 100 messages per second, and we are consuming these messages and sending them to upstream service B for processing. Upstream service B with its current scale can only handle up to 400 requests per second, let's assume. Now let's say suddenly the ingestion rate jumps to 500 messages per second. What do you think will happen? So basically, in that case, as the upstream service B was only able to handle 400 RPS with its current scale, and we have sent all the throughput directly to the service, it can get overloaded and crash. So in those cases, we should gradually ramp up the consumer throughput, even if the ingestion rate spiked suddenly, so as to let upstream service B scale gradually. So worker controller provides gradual or dynamic rate limiting via gradual throughput control. So as you can see on the graph on the left, the ingestion rate spiked suddenly, but still the consumption rate was gradually increasing. So if worker controller suddenly sends all the ingestion throughput to the upstream service, it cannot have enough capacity yet, and it can crash. So by ramping up the consumption rate gradually, we'll let the upstream autoscalers or HPAs to provision new ports and scale. It also prevents cascading failures. Now let's see how do we implement this in worker controller. So in worker controller, apart from the consumer nodes that we saw earlier that are being used for scheduling these Go routines, we also have a component called control plane, which is responsible for enabling this feature, gradual throughput control. So control plane has one leader node and two standby nodes for fault tolerance. Leader takes a lock in the database with a TTL, and when leader goes down, it revokes that lock. Control plane is basically also responsible for monitoring health of the runner nodes. So it always notes which nodes are active. Now let's see how this all comes about and how gradual throughput control is enabled via this control plane. So all the consumer proxy nodes, as you can see on the bottom, needs to respect the global rate limit that we have set for each process. So all these nodes send their current consumption rate to the control plane via update process info RPC. And then leader node does an assignment to decide what is the RPM that each node should consume at. And then they fetch these assignment using fetch resource assignment RPC. Let's see an example to understand this better. So in gradual throughput control, here we have two consumer nodes, each consuming at 300 RPM. And the total RPM is 600 RPM, as you can see on the top. Now, let's say a new node C comes up. What do you think will happen? So basically, this new node will register itself with the leader node via heartbeats. leader node will see that a total of 600 RPM needs to be distributed among these 3 nodes, and it will distribute this amongst these 6 nodes via this, like 200 RPM each. This is so that the RPM is distributed equally amongst node, and the total rate limit, that the global rate limit that we have set, 600 RPM, is respected globally. We saw how worker controller implements rate limiting. Now let's look at some of the other features that we have to offer. Poison payload handling. So a poison payload is basically a corrupted message that keeps failing during processing. So if you don't handle it properly, the consumer keeps retrying the same message again and again, and it can create an infinite crash loop and block the entire queue for processing. Our solution is simple. We track the retry count for each process. So as we have decoupled consumer code from the processing code, we call the processor, and we keep track of the retries that we are doing. And once the maximum retries are reached, we move the message to dead letter queue. This isolates the bad message from the queue, and while allowing the rest of the queue to consume normally. Failed message can be retried later. We also have context-aware routing. So messages in Kafka or SQS can carry context headers. So for example, in this case, we have X environment testing or X environment prod. So while producing, you can set these headers. And worker controller, while consuming these messages, can inject them into the outgoing gRPC message header or HTTP header. And then, based on that header, load balancer or Kuma service mesh can route these to the respective services, like production service or testing service. This can enable multiple features, like environment isolation or zonal routing. Now let's see some of the advanced features that we have recently built. Process assigner. So in worker controller, if you have many consumer proxy nodes that are running, but let's say a topic only has few partitions. But if you create the client on every node, some of the consumer nodes may not get assigned any partition at all. This can lead to a lot of wasted resources and high number of open Kafka connections. Those connections are essentially useless, but still consume broker resources and cause unnecessary rebalances during scale up or scale down of consumer proxy nodes. Without control, if we have n nodes and m topics, it can lead to n times m connections, which doesn't scale well. To solve this, we use rendezvous hashing. So each process is assigned to only a subset of nodes. Only the selected nodes create Kafka connections for that process. And when a node scale up or scale down, only a subset of process gets reassigned, minimizing disruption while significantly reducing Kafka connections. So in this case, you can see P1 and P4 are assigned to node A and not all of the nodes, and similarly for other processes. So after making this feature live, we saw a significant reduction in Kafka connections. As you can see, 40% of the active Kafka connections dropped. CPU imbalance. So Kafka's default rebalancer or partition assigner, you can say, is not aware of the rate at which the partition is consuming at currently. So we can say it is RPM unaware. So if a few partitions have very high throughput and they get assigned to a node, it can lead to a hot or CPU bound, while other nodes may remain mostly idle. That leads to throttling on hot nodes and wasted capacity on cold ones. To fix this issue, we implemented our own RPM-aware Kafka rebalancer. It distributes these partitions across the runner nodes so as to balance the CPU load. This leads to better overall efficiency of worker controller nodes. Now let's look at some of the key metrics that we use to monitor health of our worker controller system. So first we have control plane leader activity. It emits a metric each time it runs assignment of resources like rate limit. If the leader goes down, we get an alert. This is important to monitor CP health in case of downtimes. CP is basically control plane. We also monitor go routine or processor count. So as you can see on the right, we have an auto-scaling threshold at 70%. So as you can see, processor counts are scaling gradually, and all of the time, utilization is kept below the threshold. And similarly for consumer nodes, you can see as RPM increases, consumer nodes scale and scale down accordingly. So to conclude this talk, let's recap some of the key benefits and the future plans that we have for worker controller. Benefits include canary support. Push-based architecture enables canary for workers, so we can deploy with confidence. Better Kafka scalability, as we allow concurrent consumption per partition for unordered throughput. Gradual throughput control, it saves us from burst traffic and lets upstream scale. Seamless onboarding of consumers. You just have to add a config in worker controller, and your consumer is onboarded. Poison payload handling by default. Currently, we have around 1,200 active consumers, and around 100 services are onboarded. We have reached a throughput of around 50 million RPM at peak. Future plans are to increase coverage to all consumers in eternal and make worker controller open source. Any questions? Mm-hmm.
Let's say this CPI call here, due to some network failure, fails or something, then won't we be using message?
So that's a good question. So I can repeat the question. So basically, he's saying that while consuming in the consumer code in worker controller, do you commit the message as soon as you consume it, or you wait for the processing of the message? Because if you commit the messages earlier, and if the failure happens in between or the consumer node goes down, then it can lead to a failed commit, basically. So basically, what we do is we commit the message after we get an acknowledgement from the processor. We do manual commit after.
So for every event, you bring a manual commit?
Yes. So in Kafka, you have to do manual commit, but it is lazily committed inside the library. Yeah.
So like when you see like unordered Kafka, like the traffic, like you're balancing, if this go to that slide once again. Two slides. Where you had two slides, like one for CPU balancing and one before that actually. No. There were two slides, one for yes, the window is roundable.
Roundaway hatching, yes.
This one. So trying to understand if this one, like let's say if I have 5 partitions, and the problem we are trying to address is when one partition is loaded but other 4 are not, like are being empty. So what we were doing in this is like we are saying that you will assign like I didn't get this part.
So cool. So in processes, I think they can take this one.
So this is basically, let's say if you have a Kafka topic with only 3 partitions, okay, and you have 10 consumer nodes which are running. So now, so we have opened a Kafka connection in all the consumer nodes, let's say. So we have 10 active Kafka connections open, but our number of partitions is very less. So even like at max only 3 Kafka connections will actually be assigned a partition, right? So rest of the connections are basically useless because they'll never be assigned Kafka connections. So first of all, we have extra active Kafka connections open here. Also, in these extra Kafka connections, even if a node which does not have a partition assigned to it goes down, still a Kafka rebalance will be triggered. So there is basically constant disruption happening with extra rebalances. So both of these issues are solved with rendezvous hashing. So here basically, if we have 3 partitions, we'll not create Kafka connections in all the nodes. We'll only create some nodes, only 3 nodes or 6 nodes, let's say.
Remaining will still be idle, but even if they go.
No, remaining now don't have any active connections basically.
Consumer group now has only 3 consumers.
3. Before also it had only 3 consumers, but we had more connections.
Basically, we don't create the client itself.
Got it. Also, one more thing, like, are you ever increasing the
So partition scaling is not handled by worker controller. So if you have an ordered throughput, ordered topic, then you'll have to increase partitions manually.
Increasing, there's no support.
So yeah, that is part of the producer's or consumer's contract.
Just one last question I have. Like, if you can go to the next slide. CPU imbalance one. So here we are saying like, let's say on one partition, if you have heavy load, so now that consumer is like having, so the CPU imbalance you're saying is at the consumer side, basically.
At the consumer side.
Consumer side, so that consumer is overloaded because there's only one partition. So now you're saying that you'll redistribute like the assignment, consumer to partition assignment, so that the CPU gets
Exactly.
balanced. But just one question, like internally when you like reassign, you'll be doing a rehashing inside, right? And that's a costly operation.
Basically, Kafka, so rebalancing happens in worker controller also. We don't do this greedily. We do it in a way such that to reduce the load. So we do it only when there is high load, and we see that this particular node is heavily loaded. Then only we do this, and for those partitions only.
Okay. Can all these operations get audited somewhere, like what?
Huh. Yes.
That must be some time series DB.
Yes.
Cassandra.
Actually, we use ClickHouse.
ClickHouse. Thanks.
So we have questions from online. Nanda has following questions. I will ask them and you can repeat them as well. Switching from pull model to push model, especially over HTTP and gRPC, wouldn't compromise the overall latency? That's the first question.
So that's a good question. So question is basically switching from pull to push, will it compromise the latency? So yeah, it will actually add a little bit of network latency, and we have taken into that account. For that, I don't think there is a better solution, but you can do zonal routing to somehow reduce this. In practice, it is very less that we have seen.
Second question. You can pull hundreds of messages per second. You can keep up with the same consumption rate in the push model as well?
So basically, I don't think I understood the question. Can you repeat this one?
Basically, you can pull hundreds of messages per second. Can you keep up with the same consumption rate in the push model as well?
Yeah. So as we saw earlier, so the question is, in the hundreds of messages per second example, can you, in the pull model, can you do it with the same thing in the push-based model also? So yeah, I think we can do that. We have benchmarked it at 50 million RPM, and we haven't seen this issue in any of our consumers yet.
And last question, do we need the canary consumer proxy / worker controller alive even outside of the deployment window, meaning all the time?
So what it does is it consumes every time. So not during deployments only it is required. It is required whenever you want to consume anything. So as we saw earlier, Zomato is always running. You are always getting notifications. So the consumers are always running. So you need this worker controller setup to be always live.
These are questions from Nanda online.
Any other questions?
Actually, I just have one question. In your previous slide, there were places where you mentioned that these services can at max handle like say 200, 300 RPM. How are you coming up with this number? And during registration, is this also given as metadata to the
So as we saw earlier, this is just for example. Like we are giving an example. Like for example, it is able to handle 400. But in practice, most of our services have auto scaling configured. So auto scaling, what it does is it adds ports based on CPU usage or memory usage. You can configure. So we have like it can handle 3x throughput in 10 minutes. So it can't handle like 5x throughput in 1 minute. So we need gradual throughput. In worker controller, we have two configurations: minimum RPM and maximum RPM. So you can configure both of them. Minimum RPM is basically what your service can handle at minimum scale. So even at night time, if there is high load on the Kafka topic, it can handle up to minimum RPM, and worker controller will start from that RPM only. And it will then scale gradually, and you can configure how fast you are scaling also based on your service's auto scaling thresholds. So every service can tweak based on their particular usage. Yeah,
Yes.
idempotency is required as well as able to handle same messages. Yes, yes. Yes. Huh. So we do support batching as well as parallel consumption from a partition. So open source solution, I think we can go through. Some of the open source solution is basically Uber has created its own proxy, U-forwarder, and Wix also does a similar kind of push-based model. Both of them have their own advantages and disadvantages. For example, Uber mostly follows the second approach that we saw, like creating a proxy, consumer proxy for each of the queue. And similarly, Wix, what it does is, for multiple consumers, it first fetches the payload from the topic, it caches inside a local disk, and then consumers read. So basically what it does is, for example, if you have multiple consumers and only a single topic, then it only fetches once. So it reduces some load on the brokers.
Throttling part, you said like when your incoming ingestion rate increases, you will throttle it like before sending it to the producer. You will throttle it and gradually increase it. Might be a naive question, but how do you like? You must be having some monitoring service, right, which is detecting the rate that is Prometheus metrics based or like how. So whenever you're reading from your Kafka, you must be emitting some metrics that these many, for example, messages are being read, right? Like now, if the number is increasing, that's when you need to throttle rate. So for that, like the way you detect like the traffic is increasing, you like the architecture there is it like you detect from metrics or like what?
So internally, we use control plane and DynamoDB to store rate limits. So in workload control, we have rate limits, and we start from minimum rate limit. So even if the ingestion rate spikes, we start from this minimum rate limit only, if the consumption rate was down. And then from that rate limit, even if the ingestion rate is, let's say, 10x or 20x, we only increase this rate limit, like, for example, 3x in 10 minutes or 3x in 20 minutes. So this is the rate. And this increase happens only when there is lag in the queue. And if there is less lag, we decrease this rate limit. So you can see like velocity and acceleration. So velocity is basically the rate limit. So currently, for example, 20 rate limit is there. So it will only set 20 RPM. And acceleration is basically how fast we are increasing this rate limit. And this is basically gradual throughput control that we have.
Slack basically.
So basically, in our poll fetches, we see how many percentage of the time we are getting a payload, and based on this percentage, we increase the rate limit.
But when you increase, how do you know that your consumers will be able to handle that?
So there are two ways. So we have circuit breaking as well as this one. So circuit breaking is basically if you get an error from the upstream, we also throttle it respectively, rate limit.
And is this dynamically?
Everything is dynamic. We don't have to like manually change it. We do. We do had some outages. Most of them was due to control plane, but yeah.
And the control plane is tricky there.
Yeah.
That's the single point of failure.
Yeah, it can be. We do have retries. So we have immediate retries. So on failure, we can do immediate ones. Everything is configurable. You can configure based on your queue. And we also have deferred retries, so delayed retries. So I think.
All right, then folks, give it up. So while Siddhant gets mic'd up, I believe we have about 5 minutes break. There is coffee in the pantry in the back, so those of you who want to, please go help yourself. Otherwise, yeah, maybe we'll do some stuff. Siddhant, go on. Hello. Okay. That's fine. That's fine. That's fine. HDMI to Type C. You take that. Yeah, exactly. Take this. Put it there.
Once you're done, to pass it on to Anand. Yeah. Yeah. Just be careful while sitting because the recording should not stop.
Okay, okay.
Or you're putting your front pocket.
Hello, hello. Mic check. So the time, hello. Yep. So the time is 3:48. We'll start around 3:50. So make sure you're back by then, folks. Hello, hello, hello. So how much time? I have 20 minutes. Yeah, 1 more minute, folks. Hello, check. So just to gauge the audience, so how many of you come from companies where you've adopted containerization? Any show of hands? Only one? Only two? Okay, that's half the crowd. What are your deployment models? Sorry? How many of you have adopted containerized models? Like how many of you run on maybe like Kubernetes or Nomad and all of that? No? Like VMs, is that what you're saying? Okay. So for folks who are containerized, how many of you? Yeah, GKE, AWS, all of the managed Kubernetes providers? No? Okay. So among this, how many of you actually have a DR solution that is live? A disaster recovery, only one? Which company? Sorry? S&P Global. And you, ma'am? Inmobi. Oh, okay, okay. Informatica, okay. So the rest of you all just hope that everything works and the region does not go down, is it? Okay. So with that, I actually want to get to the crux of what Siddhant is presenting. So if you ever run stateful sets on Kubernetes, you know how hard it is, and he's going to demo us saying why we should not, sort of fear, and how we can achieve this through Portworx. So folks, give a round of applause for Siddhant from InfraCloud.
Thank you. Hi, everyone. So I'm Siddhant, and I am software engineer at InfraCloud Technologies. And currently, I collaborate with Portworx engineering team, specifically in the control plane team here in India. And today, I'm talking about stateful Kubernetes without fear, disaster recovery simplified. So let's go. So firstly, what is Portworx? So Portworx is a cloud-native storage and data management platform, especially for Kubernetes. So you can have any storage environment. You can have any Kubernetes distribution, be it OCP, be it SUSE virtualization, and you can have any workload. Portworx automates storage and all its functionalities for you. Adding to that, it provides disaster recovery, local HA for all your volumes, Kubernetes volumes, and also supports modern virtualization. So recently, a lot of companies have been transitioning from VMware-based VMs to actual KubeVirt VMs. So Portworx also supports transitioning to that as well, and also supports various VM functionalities like live migration and hyperconvergence. Adding to that, Pure Storage, which is the company that owns Portworx. If you are using Pure FlashBlade, which is the object store for Pure Storage, and Pure Flash Array, which is the block storage, so it has tightly integrated with those platforms as well, and it offers really good performance. So this is a gist about Portworx and what I'll be demoing DR through Portworx Torque. So let's go over some key features and components of Portworx Enterprise. So firstly, we offer zero RPO disaster recovery with PXDR, especially in the case of Metro DR. In case of asynchronous DR, which we'll be covering forward, it depends on how are you replicating your workloads to the destination cluster. And what is RPO? That also I'll cover in the next slide. High performance storage with PXStore v2. If you are having an IO intensive workload, then we have a PXStore v2 that is really performant for that. It has integration with Pure Storage, Flash Array, FlashBlade, I discussed, modern virtualization capability, and automated capacity management with autopilot and cloud drives. So let's say if you're using EKS or you're using GKE, then you're having cloud drives that are configured. So if you need to add a new volume or if you need to add a new workload, then you need to go to the console and you need to click and do everything. But it automates everything for you. If your actual cloud drive, it is consuming a lot of space and the number of pods that are consuming require more space than that, then it automatically resizes the drives for you. It automatically adds the drives for you as well. Adding to that, there is a concept known as hyperconvergence of workloads on the cluster. So let's say you have a storage on Portworx and you have two nodes. And on one of the node, your actual storage volume is attached. On another node, the volume is not attached. Then the pod, if it gets scheduled on the second node, would have a better performance comparatively than the first one, right? Because it will have a better data access performance numbers. So Portworx Torque also helps in that. It helps you basically in intelligent pod scheduling and data locality. Okay, now done with Portworx Enterprise, let's discuss why does disaster recovery actually matter, as the host shared. And adding to that, there are some incidents that have occurred. 2025, October 1st, Korean government cloud storage system, it faced fires and there were no backups available. GitLab had backups, but they were not actually restorable in 2017. They lost 6 hours of data due to that. We say that regions are very safe. They cannot be disrupted. But in 2017, an actual incident happened in which the whole region S3 service was affected. Recently, March 1st, due to the recent geopolitical situation, there were data centers that were creating sparks and fires, and they were impacted by the objects that we all know. So, so these are the recent incidents that have happened. Let's see what are the operational aspect of like handling DR. Like, why does it actually matter? Kubernetes handles stateless workloads really well, but for stateful, it doesn't have any out-of-box functionality. PV and PVCs do not like magically replicate to the destination. They're in the source cluster only. CSI snapshots are also not cross-cluster aware. You cannot tell a snapshot, okay, go restore into the destination cluster. Manual failover procedures, they are error-prone and slow. Like, you need actual engineers to go there and to do that. It's hard at that time. Adding to that, there is reputation damage and there are compliance risks. And also there are financial aspects. According to one of the study, like around $14,000 per minute was the cost that came out to be due to this disaster recovery incidents. So it actually matters. Okay, now since we have covered that and we are on a single page maybe that, okay, it does matter. Let's cover some of the basics of the DR and then we'll go to the demo. RPO and RTO, what is that? Let's say this is time. Disaster occurred at this point. This is your point of last data sync. And the time between that, or basically the data that you basically lost due to that, that is your recovery point objective. After some time, your systems came back online. The time between that, that is your recovery time objective. So this is basically RTO and RPO, what we know in the DR terms. There are two famous DR architectures that we currently have. Active-active, in which you have a global load balancer. You have, let's say, 2 data centers. And on the first data center, you have a front-end app, stateful workload, you have a storage. On the second data center also, you have the same. And your load balancer is basically distributing the workloads among both the data centers. So if one of them goes down, another serves the traffic really well. So there's no issue here. And the stateful workload is getting synced periodically. In active-passive cluster, this is not the case. You have a source cluster or the data center 1 that is actually serving the traffic. If it goes down, something happens in the data center 1, then the traffic gets diverted to the data center 2, and you'll need to actually basically start the workloads there. They are in the scaled down state in the destination. Okay, now let's discuss 2 DR strategies that Portworx offers, asynchronous DR and synchronous DR. Asynchronous DR is cross-region friendly, like if you US East one, US West one. So if you have like data centers in a wide area network, then you should configure asynchronous disaster recovery. The RPO for Portworx that we specify, it is 15 minutes. And like it depends on the schedule or the schedule policy that you set, which also I'll be covering in the demo. And recovery time objective is less than 60 seconds. It also depends on the workloads that you are actually using. So this is a small overview of the async disaster recovery setup. You have a source cluster, you have a destination cluster, and in between, it's an object store. It can be S3, it can be NFS. Basically, all the volume data is firstly uploaded to the object store. We call it the cloud snapshot backup. And then, at the same time, the volume data from the object store is restored on the destination cluster. We call it as cloud snapshot restore. In short, cloud snap backup, cloud snap restore. And the Kubernetes resources, the stateful set, deployment, specs, all these things, whatever you have in the Kubernetes, they are at the same time applied to the destination cluster, but in a scaled down state. Let's say you have a deployment that is running 2 pods in the source cluster. We apply the deployment on the destination, but with 0 replicas, so that we are not actually running anything on the destination. Kind of an active-passive setup. And synchronous disaster recovery is basically only recommended when you have the data centers in a metro area network, like within 50 kilometers of range. Only then we recommend this. And the RPO in this case is near 0. And the RTO is less than 60 seconds. So in this case, as I said, the network latency should be less than 10 milliseconds, or it should be in the metro area network. And how the deployment happens in this case is you have a stretched Portworx cluster across both these Kubernetes clusters. So actually, it's a single Portworx cluster. If you create a volume in the source cluster, a replica of that volume gets automatically created on the destination cluster. And any write going to the source cluster will get replicated at the destination cluster. So anytime you have an issue in your source cluster, if you scale up the destination cluster, you have the actual latest data. You won't be losing any data here, because every write goes through both the sites. And this is like especially recommended for products that are very sensitive in terms of their data, like maybe the banks or the trading systems. OK, let's do a demo about Portworx DR and using Stork. So Stork is the actual product in the whole Portworx deployment that actually helps in the disaster recovery. So it is a short form of storage orchestration runtime for Kubernetes. OK, so firstly, I'll be demoing async DR, and then I'll give a short brief overview of the metro DR setup. So I have the terminal. It is a blue-green setup. This is the source cluster. That is the destination cluster. And OK, so these are two harvester clusters, or SUSE virtualization. This is source, and this is destination. You can see it is basically 6-node cluster. And yeah, and this is the app that I have deployed, basically. It is a pizza shop app. You can start auto orders here, basically just to fill up random data in my PostgreSDB. And yeah, now I'm starting my orders. So it is generating orders currently. And I have deployed this application in the DR demo namespace. You can see there are two PVC. One is the Postgres PVC, one is the VM PVC. So basically, there are three workloads: front-end, Postgres, and Word Launcher. Word Launcher is basically a KubeWord VM in which I'm running a Flask backend app. So there are three things. OK, now I'll just show you how Portworx interacts with the PVCs. So each PVC has a storage class. And in each storage class of those PVCs, we specify the provisioner to be pxd.portworx.com. So in the first PVC as well, and in the second PVC as well. This basically hints that Portworx will provision the volumes for these persistent volume claims. And here we can see that Portworx is running in the kube system namespace. It is the storage cluster CRD that actually reflects, OK, the Portworx is running. These are the Portworx pods. Similarly, in the destination, we have Portworx pods running, and Stork as well. So this is the source. And yeah, so currently, we are generating orders. Next, what I have to do, I have to actually pair these two clusters so that they know each other, and they can basically migrate the workloads from one to another. So for that, we have a custom resource known as cluster pair. In each cluster pair, we are basically putting the kube config of the destination, and we are specifying the backup location to basically which object store I want to back up my volume data to. And the backup location CR looks like this. It is an NFS backup location that I'm currently using. And the secret, or basically the actual credential of that NFS backup location, it is stored in a secret, Kubernetes secret. It has to be created in both source and destination. Now, OK. So as we can see, currently in the source, we have these pods running. But in destination, I don't have anything there. I even don't have that namespace. And the orders are still generating. Now I'll basically stop that, and I'll do a DR migration. And we can see it is 187. Now I'll create a migration schedule. So migration schedule is basically a schedule that you can say, OK, you need to migrate these namespaces in this frequency. Like after every 15 minutes, you need to migrate namespace XYZ. So currently, this migration schedule is migrating the DR demo namespace, and it is using this schedule policy. Every 30 minutes, it is basically migrating that namespace. And for this demo purpose, I've created a local nginx config. So firstly, it is pointing to the source. And if the source doesn't respond, then it basically falls back to the destination cluster. So OK, now I've created the migration schedule, and the migration has started. I'll just forward it. Currently, as you see in the volumes, like it is currently migrating the volumes, and then it will move to the application stage. Volumes is basically the actual volume data, and applications is the actual resources or Kubernetes resources. So you can see the stage is volumes, and it is in progress. OK, now it has gone to the application stage, and it is still in progress. OK, now it has been successful. Let's see in destination what has come. In destination, we can see there is a PVC, and there is the deployment, but there is no pod. So the workloads are not actually scaled up on destination. And you can also see there's the KubeVirt VM as well on the destination. OK. Now, basically, I'm showing that, OK, all the nodes are online in the harvester cluster. Now I'll basically shut down all the workers in my source cluster. So firstly, it will scale down all the workloads, basically all the front-end, Postgres, everything. And also, it will basically kill all the worker nodes on the source cluster. So currently, they are active, and my app has been disconnected. It is now giving 502. Now I'll do failover on the destination. I'll use stockctl perform failover command with the -- skip source operation. So it will not do anything on the source. It will just scale up my workloads on the destination cluster. So as we can see, it has completed. Currently, it is still giving 502 bad gateway because the KubeVirt VM that is running in the destination, it has a cloud init script, so that will take time to actually come up. So I'll just forward it. As you can see, currently, the nodes are unavailable, or basically, they have been killed in the source cluster. Yeah, now the app is live. And currently, it is serving from the destination, not from the source. And it started from 187. Now it is going ahead of that. So this is an example of asynchronous disaster recovery. Because here, one caveat can be there. My migration has completed. After that, also orders were coming in. Let's say after 187, order could reach up to 250. But the thing is, we only migrated till 187. We didn't reach till 250. So if I did a failover, then I would only have the data till 187. That is what RPO is. That's why we say we do not have a 0 RPO in async DR, because some data might be lost. If your migration schedule is configured every 15 minutes, then 15 minutes data can be lost at a time in destination because you haven't received that. But in case of sync DR, that is not the case. So this is an example of async DR. I'll just give a brief overview of the async DR demo as well. So for sync DR, I'm using 2 OCP clusters. One second. I have deployed the same app, basically the pizza shop app, on the source cluster. And it is currently running. I'll start the auto orders. Same thing, I'll just create the cluster pair. And I will start the migration schedule to start migrating. One catch in sync DR is, I'll just show. Yeah, here the storage status is not provided, while the scheduler status is ready. Scheduler status is basically, OK, Stork can talk to the Kubernetes API server. Storage status is from Portworx side, if Stork can actually communicate with Portworx or not. Here, Stork actually doesn't need to communicate with Portworx, because the volume data is actually getting replicated by Portworx every time. In that case, in the async DR, Stork actually needed to start a Cloud Snap backup and restore. But here, it's not needed. That's why it says not provided. This is a migration schedule. It is migrating the same namespace. And here, OK, it is successful. Same thing, there are no pods in destination, but all the deployments and everything are there. OK, now I'm basically turning off all the master nodes in my OCP cluster in source. So it is scaling down front end, scaling down Postgres, stopping the VM, and now it is shutting down all the master nodes. Okay, it will take some time for all the nodes to go down. Okay, now when I do a kget nodes, it is basically showing some, okay, yeah, API server issue. So basically my master nodes are not working in source. Now I'll start a failover in the destination. And okay, 502 bad gateway. So failover has been completed, and the app will take some time to come up. Why? Because there can be some transient cases when the control plane is actually not down in source. There might be some transient issue. So Stork tries to actually communicate with the API server for around 2.5 minutes. Once it doesn't respond, it just directly scales up the workloads on destination. So I'll just forward it. Oops. Okay. Login incorrect. Okay. I think it should be up from now. Yeah. So 502, and then I refresh. It is like showing the data. And this data is the actual data that was there in source. It is not like after 15 minutes or something, some data has been lost. This was the actual data that was there in the source cluster volumes. So this is like a demo of SyncDR. I'll answer any questions afterwards. I think you might have. So just a brief, like, OK, how do we protect data in Kubernetes? So let's say we have a pyramid, and this is the level of data protection. It goes upwards. Firstly, you should have local HA. Like if you have a cluster, and there are multiple nodes, let's say 2 of your nodes go down, and your pods get scheduled on the 3rd node now. Your storage should be available there. Your volume should be available there. So Portworx provides that, and that is the minimum that we should do. Now, after that, what should we do more? We should add backup and restore. Anything happens, we should be having the backups, and they should be restorable on the destination. OK, we got this. Now what do we do next? How to protect it more? Let's say we have data-intensive workloads. We cannot lose data. In that case, disaster recovery. We should be having RTO and RPO tuning for our data and our workloads in the clusters. OK, let's compare Portworx DR with some of the solutions that we have currently. Velero, famous open source project by VMware, and it has a backup first approach. It is a backup restore solution. It is not a DR first approach solution for us. You need to actually back up, and then you need to restore all of that data at once on the destination. Not like Portworx DR, where each snapshot is getting uploaded and at that time getting restored to the destination. As I said, better for backup, restore, migration. It also supports failover and failback, Portworx DR. Velero has more manual steps and operator steps, while Portworx DR can be automated. You just need to run storkctl commands. Longhorn, famous product as well, and like really great open source project. So it offers DR, but only for the storage volumes, not for actual applications that have been deployed on Kubernetes. It also has manual failover and failback, but Portworx has like full cutover automation. If your load balancer is configured to basically, like I just demoed, you can basically cut over your whole traffic from source to destination anytime. Longhorn has longer downtime if using backup and restore workflow. Like that's obvious because you'll need to restore the whole data at once. But in Portworx DR, we have scheduled migrations going to the secondary. There are other solutions as well for DR, K10 by Kasten and Twilio. So that is also mostly backup plan-driven DR. I'm not saying that those are not good, but they are good only for backup and restore workflow. For actual DR, like I don't think they are that good, or they don't support those capabilities. While Portworx DR, it supports both Metro DR and async DR. And in these, we need to recover using the backup artifacts. But here, as I said, we are directly keeping the destination cluster warm by our migrations. And These are best when basically the goal is data protection, backup, restore, recovery workflows. Portworx DR is best when basically goal is repeatable failover and failbacks for stateful apps. And these have like weaker integration with the underlying data management software. But Portworx DR is stronger because the underlying infrastructure or the Portworx, it is managed by the same software. So it is better integrated with Portworx. Okay, getting started with Portworx Enterprise, if anyone of you want to like just explore it or try it once, there's the enterprise website. You can just scan the QR code. You can go there. You can just read about that. There's Portworx Enterprise documentation that you can check out. And this is the sales number if anyone is interested. Just kidding. About InfraCloud. So if anyone work in the team or if any org is looking out for help in these domains, cloud native, product engineering, platform engineering, site reliability, observability, DevSecOps, application modernization, so we can collaborate. We can discuss at this website, contact us, or you can chat with me. I can share the details. Thank you. This is my Twitter and GitHub. Any questions? You can use this.
No, it's okay. Check. Okay, sorry. So folks, I'll be handing the mic over. Please introduce yourself, then ask questions. Yeah, go on. Floor is open. Anybody have questions for Siddhant?
So in this sync DR, I think the service was down for around 2.5 minutes, right?
Yeah.
So can we say that the RTO was 2.5 minutes there?
That's a valid point, but I think there's a flag as well to skip that actual checking in the source. We can skip the source operations.
Okay.
In that case, it will just scale up on the destination.
So in that case, both of the source and destination are up all the time?
No, source will be down. Destination, you will scale up. Source will be down only, then you will need to do the failover to the destination.
Before the failover?
Before the failover? No, the destination will be scaled down. It will be basically a passive cluster.
But it will still take some time to scale up, right?
Yeah, it will take some time. So that is RTO. So in that case, we say that RTO is 60 seconds, or basically how much time the app takes to
Got it. Thanks.
Any other questions? All right, folks, give a round of applause for Siddhant.
Thank you.
So while we made it to the end of the meetup, so while Anand gets mic'd up, I just want to have a couple of announcements. So one thing is we, as the platform engineering meetup, also have our DR strategy. We have one happening next month in Pune, April 9th. And yeah. Yeah, we have it in, Mumbai actually. And in Bangalore, we will again have it in May. So for those who are interested, please, I would say, come ahead with your proposals. And we're also looking for reviewers. If you really think that, hey, I can sit on the panel and provide, actual good feedback for folks who are actually going to present, we welcome that as well. So if you're interested, please maybe reach out to Zainab or myself. Yeah. So one last thing is, okay, he's miking up. Yeah, the last thing is, you good?
Yeah. Hello.
You want to connect? So doing some witty stuff. So how many of you get paged at 2 a.m. in the morning? Anybody on call who face outages at 2 a.m.? Perhaps, yes, okay. Yes, the gentleman in the back. What is your name? Sorry, could you stand up maybe? Your name, please? Vignesh. Your company? PhonePe. Oh, wow. How ironic. So what do you tend to do at 2 a.m. in the morning when you receive this? First instinct would be just turn off your phone, but what do you actually do?
I'll check the logs, basically.
Okay.
What is actually causing the issue.
Okay.
Most of the time it will be the issue. The issue is with the developers. They'll
So, question regarding this: how many of you represent like platforms team, SRE teams, DevOps teams? Show of hand, please. Okay. And what is the other faction? Are you all developers? So basically, you're causing him to get up at 2 a.m. and just for revenge, he sort of kills you off at 2 a.m. So thanks a lot, Vignesh, for this. And without further ado, folks, I'd like to introduce this talk. This is Srinivas Anant. Let him introduce himself. But basically, he's going to talk about how we deal with alerts, don't cause any fatigue to either developers or the platforms team, and how we can do it in style. So yeah, take it away.
Thank you. Yeah, hello everyone, I'm Anant. Today I'll be walking you through how you can solve your alert fatigue problem in your environment. So a quick intro about me. I've been senior member of technical staff at Nutanix for the past 7 years. So to get started, I'll just give a quick intro about Nutanix and what we do. So previous stack which we normally have is basically where you have compute, storage, networking, which are all separate and siloed. And Nutanix pioneered the hyperconverged infrastructure where everything is combined together to form one big stack where managing all of them is much more simpler in the data center. And we also have a hybrid multi-cloud where you can run workloads on your cloud as well as on-prem, and it's easy for you to move across cloud to on-prem and also give you tools to operate them across environments. So what does it include to have Nutanix as a hybrid multi-cloud? So first is you would use your own hardware, whichever is available in the market, and your choice of hypervisor, which is, you could use AHV, which is our own in-house built hypervisor. You could use ESXi and Hyper-V, VMware and Microsoft. And you could also deploy it on your own cloud, whether it could be Nutanix's cloud, or you can even do AWS, Azure, wherever you would want to deploy your applications. And also your choice of Kubernetes platform. It could be NKP, which is Nutanix's own offering, Nutanix Kubernetes platform, and you can have Azure and AWS. So this is a stack of what we are. You have your low level where you have your Nutanix infrastructure, and on top of that you have your storage solutions, database, and your Kubernetes platform, and your Nutanix Enterprise AI. And at the topmost level is where your applications are running. All the tools like IAM, self-service, or cost governance. And the problem that we are solving is at the top level, where it's on the deployed for the applications that are running on your environment. So before I get to the problem, I just like to explain the reasons and the evolving of our stack from how we have come to where we are. So when we started off, we started multiple microservices started emitting telemetry data, which is basically logs and metrics. And that's when we started running InfluxDB and Elasticsearch. And what we noticed was that the existing infrastructure was a bottleneck, especially InfluxDB, because it was a single node that we were running. And it was getting bottlenecked with the amount of system and application metrics that we were sending it to. That's when we decided to pivot and deploy Victoria Metrics, which is a very known open source tool, and it provides clustering out of the box, and it has multiple components which can be scaled separately. And now that we have the trifecta where we have logs, metrics, now we decided that between microservices, you didn't know when one microservice is talking to another microservices. So that's when we decided that there was no visibility into the dependency between two microservices or more. And that's when we implemented distributed tracing. We used the Jaeger stack. And after this, we realized that we have alerts and metrics coming from different sources. And that's when we realized that we don't have a single point to consolidate all these alerts or send it to different developers. That's when we found an open source tool called Clutch by Lyft. It is similar to Backstage, where we built a module on top of it so that we can consolidate all these alerts and send it to developers. So as I said, the main problem statement is that when you have multiple sources, your alerting is completely fragmented. You have sources coming from Grafana, Alert Manager, OpenSearch, or KTS events. And all of them are being sent to different Slack channels or different teams in general. And no one knows what's going on in your infrastructure. And this essentially causes alert fatigue because let's say you have alerts coming from microservice A and microservice B and they're going to a single Slack channel, developers don't know what is happening. They'll get confused as to who owns which microservice. And they'll end up muting the Slack channel because they don't want to look at it anymore. And also, because of this, there's no routing in general. As I said previously, you don't know where the alerts are going in general. And the developers will not sit and create alerts, they'll worry about where to send the alert to. This is a very pain point because that is not the responsibility of the developer to send it to the right Slack channel or anything. That should be defined pre-hand. And also, on-call and incident management becomes hard. Let's say at around 2 a.m., you have some microservice breaking, you don't know who to reach out to, who's the right developer, who's the right team to talk to in general. And there's no ownership as to who owns what. So this is a scale at which we operate. We have 6+ teams and 10+ environments and around 500 applications that we cater to. And this is the amount of data in the metric stack and then around in the logs. So for a solution for this, what we decided was that first we will consolidate all the alerts coming from different sources. You have KTS events, Grafana, Alert Manager, whatever have you. And then we also wanted to make it plug and play. Tomorrow you have another source and a destination. Let's say tomorrow you have PagerDuty, or let's say you want to send it to an email. That could be more plug and play, and that's where we wanted to solve that main problem. And also, let's say there is a weekend, there is a maintenance going on, and you don't want to bombard the developers with a lot of alerts in general at that time frame. So we give an option of suppressing these during that time. And the ownership, we wanted to make it more easier, so we wanted to send it to the right team, the right product, so that they can go about and look at their alerts. And this is something I read in a book, and this sort of applies to observability a lot. Send little information, you're blind. Too much, you're blinded. So you have to give the right amount of context to developers to go and debug the problem. If you give them too much information, they'll get confused as to what exactly is the problem. And too little, they'll still be confused and they won't know what to look at. And we also wanted a centralized on-call system and rotation and escalation metrics. So every week you would have developers being rotated in a proper fashion. So here's the ensemble of how we solve this alert problem. So you have Argo CD. We use Argo CD for our GitOps approach, where everything is on GitHubs and Argo CD applies the configuration on a Kubernetes environment. And you have OpenSearch for all the logs. You can visualize and see all the logs that are coming into your system. An alert manager for your disk or some PVC that's pending state or whatever is there. And KTS even, let's say a pod is in crash loop back off or it's in an error state or anything else. And Grafana for another set of, if you want to relate it to a dashboard. And here is where Clutch sits in the middle. And Clutch receives all of them via webhook. So now what we have solved here is that all the components that you see on the left-hand side, we have made sure that all of them have one endpoint, which is a webhook. So it's easier for developers to not worry about where the alert is going, whether it's Slack, email, or whatever it is. And then Clutch processes all these events, puts it into a queue. In this queue, we it sends it and it acts as a consumer and a producer. So it will process all these events, format it in the way we want it. And also, we also have the metadata stored about which microservice belongs to which developer. So all this data, we store it. We also have data like whether they want to send it to Slack, email, or wherever it needs to go to. And then once we have this information, we send it via Slack, email, and another endpoint. Even after deploying this stack, we still had some challenges. We were still missing out on critical alerts. And we realized that since everything was now being routed via Clutch, we realized that there are still more false positives that are being generated, and we had to go back to a drawing board to understand which is important, which is not important. And also, as you can see, we have sources from Argo CD, KTS, and everything, and they're all structured differently. You can't have a single common way of alerting developers and formatting the message in general. And there are some services that change their state very frequently. Like for a second or two, they'll change their state and they'll go back to the normal state. And sometimes this can cause noise, and developers will again go and mute the Slack channel. And as always, anything new, we have to get everyone onboarded and understand the system, that this is a better system to use. And we also didn't have severity levels across the board. A severity level for team A was not a severity for team B, so we had to figure that out. So we still have not talked about the on-call system. So to fix this on-call system, we decided to build an in-house tool called Uptime. So where we have the UI present, where you can create health checks for any service, whether it's running on an EC2, whether it's running on a pod. And once the developer comes and creates a health check, it pushes that message to NATS. Again, the Uptime behaves as a producer and a consumer. So once it's in NATS, it's also stored in timescale DB. We use timescale DB behind the scenes for historical data. So let's say in a past 1 week, how many times a microservice went on. To gather this information, all this data is stored in timescale DB. And once a health check fails, we send a notification via email and Slack and also via phone call, so that developers are more proactively look into the issue rather than reactive approach. And as I mentioned previously, we had some critical alerts that we kept missing out on. Let's say a disk space alert occurred at 11 o'clock at night. No one's online to look at it. And by 6 o'clock, it fills up and the server crashes and it's not reachable. So what we decided to do was we leverage this on-call system as well for normal alerts as well, not just for health checks. So let's say a disk space reaches like 90% threshold, the alert immediately goes to the developers team saying that, hey, it's at 90%, you have to look into it right now. And the impact of building the system is that we have processed around 200 kinds of alerts for so many teams. And this has also led to the decline of false positive alerts. And the alerts are more organized and people know exactly what the issue is. And as I said before, the time to resolve any critical issues has reduced from 30 to 6 minutes. And now it's easier for developers to create rules. They just have to go to Grafana or Alert Manager and create their alerts rather than worrying about where the alert is going. And this has, obviously, it has reduced our alert fatigue for all developers. So here's a screenshot of how an alert looks. So as you can see on the left-hand side, we have an Argo CD alert. We tell the app name, the namespace, the cluster, and what is the status of the app and the sync status. And we also give the latest commit. So developers know who made the last change for it to go into this kind of state. And also, this is an alert manager alert. So as you can see, we have grouped alerts, 3 alerts into one message, so that we don't bombard the Slack channel with like singular alerts. And this is easier for them to look at what is happening. And also, we have given a silence link as well. So when, let's say this is a maintenance window and they know that something is down, something maintenance is going on, node is restarting, so obviously the PVC has gone into pending state. So they can go and click on that automatically for, let's say for few hours, they can silence the alert. And this is a OpenSearch alert. So this is, again, very intuitive in general. We've hidden this out, but the pod name contains the link of the OpenSearch dashboard with the filter already present. So once this alert comes to the developer Slack channel, they can just click on the pod name. It will automatically redirect them to OpenSearch with all these filters already selected: the namespace, the cluster, the error level, and the container name. So developers are more likely to go and look at the alert directly. They don't have to go log into OpenSearch, then sit and filter out, okay, this is my microservice, this is the error I want to look at. So this is, along with the period start and period end, within that time frame, what is the error that has occurred for your microservice. So this makes it more intuitive, and we also give some amount of logs for them to have a better understanding what they're going into. It's not blind in general. And the last one is a KATS event. Similarly to OpenSearch alert, we also link the OpenSearch dashboard here as well, so that they can again look at what is going on with their microservice. So what are the key takeaways of building such a system in general? Now this becomes a single pane. All the alerts are being redirected to Clutch, so it's easy for you to know that where the error, any issues are occurring. So we can immediately look at Clutch and be like, okay, this alert is coming from Grafana Alert Manager, and we can go about debugging the issue. And this has solved the major problem of redirecting alerts to the right developer team. So we configure alerts and we segregate based on the team name and the product. And this helps finding root cause faster, because once the alert is there, they get redirected to the right tool and they can go and figure out what the issue is. And correlating logs and metrics is easier now, because all they have to do is look at Grafana, look at OpenSearch based on the alert. And with on-calls, with uptime, the on-call is also simplified, where you have an escalation matrix. Let's say one developer does not pick up, the next developer will pick up, so on and so forth. And the key other thing is that we have not used any vendors here in general. So all of them are in-house built tools, where we used all the open source tools that are out there in the market. Yeah, I'll open up for questions.
Oh, yeah, check. Any questions?
Yeah. Yeah, yeah. 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 It was more from an operational perspective, why we use NATs. Because running NATs is much more easier because it's running on a single server along with timescale DB. So it's easier for us to manage it. And the system that we built is pretty small. We didn't want to scale it out in general. We just have like 50 to 60 checks that we are running. So running something like Kafka will be a big overhead on our end. So we decided to just run NATs there. And so message is simple. It's just a small ping onto the pod. If it's healthy, OK. If it's not, then you can just go about and call the developer. We store timestamp as when the alert occurred, what was the error in it, and why did it go down. Those small criteria we store so that developers can look at the historical data in general. So that for further understanding of why it went down, when it went down. If we just keep it in NATs and not in timescale, we won't know what is happening. It will just health check and just come back in general. Structured data. Also the team details as to who's the next on-call developer, all the relational data as well, right? We use Postgres. It's Postgres with timescale DB as an extension. So all the time series data in timescale, but let's say the user, what is the user and the phone number and which team they belong to, all that is stored in the Postgres side of things. Yeah. Yeah. Yeah, next on-call, who's the next on-call engineer, and then we use that data to sort of alert them. Postgres, yeah.
Any other questions? Do we have questions online, Zaina? Okay. Not yet, okay. Yeah, please go ahead.
It's not really a question, but a short thing I want to ask. Like, could you go to the slide where you have Clutch and all your like other aggregators there?
Okay.
So it's something like a fun fact type. Can you go like 2 more slides back? You had Clutch and all your.
Yeah. Okay. The on-song.
Yes. So, in my where I used to work earlier, so I'm a developer and devs used to do on-call. So if you see that the Grafana, right? So as devs, when we write metrics, we don't like as a newbie, I used to just put like 8 labels, 9 labels, right? And when you do something like that, your cardinal with such a high cardinality, you're emitting like maybe 3 times, 4 times the metrics you should.
Yeah.
So, and it used to work well, but let's say today you have 400 tenants. Over the next 2 months, let's say you got 200 more tenants. Over time, the metrics are increasing, and the Grafana instance, it used to go it used to OOM.
Okay.
And how the metrics were sent to Grafana was using a prompt tail agent, basically, which would also OOM eventually because of the scale of metrics. I just wanted to ask, like, from this Clutch platform, are you also like controlling this part?
No.
This not
We use Victoria metrics behind the scenes, so all of them get stored in Victoria, and Grafana talks to Victoria and does everything.
Okay.
And we've also established that you should not send high cardinality metrics. Victoria can handle it, but we have sort of made sure that any metric that is being sent should not have any high cardinality data in it. Only important data labels should be sent in a particular metric. That is something we've imposed in general, so that developers don't send a lot of it and it gets overloaded with high cardinality data. And when you try searching it, it OM kills, like you said, right? So that we have prevented.
So if I understood rightly, it's going to some Victoria database from where it's
Grafana's
polling it.
Yeah, Grafana's polling it.
Okay. And just coming to that 2 a.m. on call, right? So there's a time like where I used to get paged every day at 3 a.m. in the night just to go and see the pods are restarted. So like one fine day we sat and you used to think, I'm getting paged, there's an OM, and the pods are restarted when we go and check any on-call.
Yeah.
So we used to think that some colleague of ours is, waking up and restarting by the time we are there. So one day in the room, all of us sat and we discussed who's restarting it at 3 a.m. in the night, right? When it goes in an OM state, OM killed. So we then checked and realized some ex-employee had written a cron job that at 3 a.m. when a 503 spike happens, you
Restart it, refresh it, and again it builds up in general.
We guys used to wake up and then just to see it's restarted.
Yeah.
And coming to this uptime thing, over there, like you're saying, these are basically K8 health check where
it could be service health checks on running on an EC2 instance as well.
Okay.
Doesn't necessarily have to be on K8s.
Okay.
Yeah.
Got it. And when you say Argo CD, that will only be covering for Helm-based deployments,
Yeah.
right? What about some deployments should be done on just pure VMs, for them, like Diesel, Argo CD will not be there. Right?
No, that won't help them there.
Okay.
Yeah. This is mostly for our use case where we have leveraged this Argo CD. Most of it is on Argo CD and few services are running on EC2. Okay. That's where basically uptime talks to that EC2 instance, detects that, okay, I'm performing a health check. If you're healthy, well and good. If not, I'll allow it to you in general.
Got it. And what is at Nutanix, what is the log retention for application logs that you're generally storing at?
I don't know if I can talk about it.
Oh,
but
okay, sure. And when the reason I'm asking is one of my previous employees, when I used to search in the logs, right? Let's say you're searching for 90-day-old logs for incidents that occurred. Let's say a bug occurred 90 days back. The Grafana instance, the Loki where we used to search, right? It used to die if you basically search for 90-day-old
90
data.
days, yeah.
So did you also have certain problems in this area? And if you did, how did you solve it?
That we have with Victoria Metrics.
Okay.
The thing about Victoria Metrics is you have a VM insert, a VM storage, and a select. So the VM insert and VM select are very stateless in nature. So you can scale both of them how much ever you want. So whenever we ran into this issue, we would either scale it up, and VM select also has the option of caching your request. So let's say if you have been doing the same query again and again, it'll start caching it. So that way we sort of did solve that issue. In case you have to look back for a longer period, we made sure that VM select is able to handle that sort of load.
Okay. Thank you.
Thank you.
Myself, Shilpa. So just wanted to check any security aspects we have considered when we do it. Because if I understand through Clutch, one can get into all the logs and the alert systems and everything.
Clutch does not show the logs, it just receives it and then processes and sends it.
So basically through Slack, it will redirect the
alerts to the right developer, and the Slack channels are pretty private in nature, so only certain developers will be added to that Slack channel and they can look at it.
Okay, yeah. I'm from Salesforce, so I'm using Slack too. Thank you.
I just like to add some more points with respect to this. So with respect to Clutch, what we did is we built a RBAC layer. With RBAC, of course, only when you belong to certain groups, you get access. So if two people are from different teams, they cannot see each other. And of course, Slack channels are private for a given team. And as well as you have, in emails, you have distribution lists, right? So everybody they have their own, they can't see anyone else's. Any other questions? Hopefully folks online are online as well. Yeah. All right, folks, give it up for Anand. So, okay, we've come to the end. There is a sequence of things that we have to do, otherwise DR will kick in. So the first thing is, I think all of you should have got feedback forms. And if you don't have pens, you can collect it from others. Okay. Apart from this, we will have a photograph session. And again, before this, we will do some shout-outs. So folks, first to start off, please give it up for our speakers once again. Give it up for Dev, Sakib. Guys, stand up. Maybe come here as well. Give it up for Dev, Sakib, Siddhant and Anant. Come on, guys. Keep it rolling. Give it up for our sponsors, Cloudflare, QuintType as well. We have Rahul in the back. Give it up for Rahul. Really interesting person I had a chat with. Probably I'll catch him after this. You guys can do that as well. From AV, we have Gyaneshwar from QuintType as well. Give it up. And we have Ravi at the back who's clicking photos. Give it up for Ravi as well. What up? Again, give it up for our panelists. Unfortunately, not many of them are there. There is Safir. I think Sudhir was there as well. For our curators, such as myself, I'm Bharadwaj. You can give a round of applause. And for Talina, who is there in the US time zone. She works for Couchbase. And for Hasgeek, Zainab. And give it up for Kiran as well. You have this crazy setup here. We have no idea how we did this, but it just works seamlessly. So, and finally, a round of applause for you all for making it here on a Saturday. Please give yourselves a round of applause. So finally, if we can just get one photo with everybody, that would be nice. Please hand in your feedback forms. And we will actually get the party started because there is samosa from Samosa Party at the back after this. So yeah, folks, maybe let's come for a photo, yeah?